Welcome to Statistics 101, where we learn statistics one bit at a time, in under 10 minutes. In this episode, I want to talk with you about discrete random variables. Let's start. Usually, people have a hard time understanding random variables, but let's try to break it down. Suppose we want to play a board game with our friends, and we need to reach some goal. In order to move forward, we need to throw a dice that has the following faces. We have 2 times a 1, a 2, a 3, a 5, and a dragon. Think about some crazy fantasy board game you are playing. If we throw a 1 or 2, we have to move 1 backward on our board game. If we throw a 3 or 5, we can go 1 forward. And if we manage to get a dragon, we can move even 2 fields forward. Of course, we are dealing with randomness here, since we cannot choose ourselves which die phase we will get. Thus, every phase of a die is associated with a probability. Since this die is a fair die, each field has the same chance to appear. Since we have 2 ones, obtaining a 1 is more probable. And basically, this connection between the phase of a die and the number of fields we have to go forward or backward can be described by a random variable. Let's move to the formal definition of a random variable. So the definition of a random variable goes as follows. A random variable x is a function from the sample space omega to the set of real numbers, given by this expression. Plus, x has to be actually measurable, but in order to not make it more difficult than this topic already is, we will leave this part out. So let's focus on the statement itself. So what is a sample space? A sample space is in principle the set of outcomes, right? And it maps to real numbers, and these real numbers are called realizations. So our random variable is a mapping from the sample space to the space of realizations. And the realizations is what we had in our board game as the fields which we could go forward and backward. And the sample space are the outcomes, which were in our cases the face of a die we would see when we throw a die. Okay, so far so good. Another 2 terms which are quite important in this context is realization, as I said. And this is denoted mathematically as the random variable evaluated at omega, and Rx, which is the support. And the support is the set of all possible realizations. We will see why this is important to know. So let's move back to our example. So our sample space is given by this expression where we have a 1, 2, 3, 5, and the dragon in it. In order not to forget our mapping from the phase value to the fields which we can move forward or backward, I've written it down once again in the top right hand corner. Can we also express the probabilities? And of course we can. We have 6 faces of a die in total, and we have only 1 number which comes in 2s, and this is the 1, right? And that is why this number has the probability 2 over 6, and the other ones has the number 1 over 6, since our dice is a fair die. Our random variable is then given by this expression, where it is equal to -1 if omega is element of 1 or 2, is 1 if omega is element of 3 or 5, or is 2 if omega is element of dragon. And this is essentially given by our mapping, which we have already written down. So it's really straightforward to construct such a discrete random variable. Let's illustrate what the probability actually is. So if we ask the question, okay, what is the probability that that a realization is equal to 2? This is actually nothing else than if we would ask, okay, from the omega, so from the elements of the sample space, which elements will be evaluated at x, which are equal to 2. And the only omega, so the only outcome which fulfills this is dragon. So the probability is 1 over 6, because we know already the probability of obtaining a dragon. And if we ask what's the probability that we get the realization equal to 4, this is actually, so we don't find any outcome which is in the sample space which evaluated at x gives us this realization. So we have an empty set, and the probability of an empty set is equal to 0. This is, why is that? This is essentially given by a Kolmogorov axioms of probability. So let's move on and define a discrete random variable. So a random variable x is discrete if two requirements are fulfilled. The first requirement is that the support of x, Rx, is countable. Means that it has to be finite or at least in one-to-one correspondence with the natural numbers. So in principle, essentially, it's like if you can count it, then Rx is countable, like the expression already says. And the second requirement is there has to exist a function px which maps from the real numbers onto the interval 0 to 1. And the real numbers here are essentially the realizations, which we described already. So for any x which is element of real numbers, the following expression has to be defined, that px of x is equal to, and it has to be equal to a probability if x is element of the support and 0 otherwise. And we can even go further and show that any function that fulfills two properties can be called or regarded as a valid probability mass function. The first characteristic is it has to be non-negative. That means for every x in the support, the probability mass function has to be greater or equal to 0. And the second characteristic is it has to sum up to 1. So if we sum over all realizations in the support, or over the probability mass function, it has to be equal to 1. Let's illustrate that on another example in order to understand what a probability mass function has to do with a random variable. So let x be a discrete random variable that can take 3 values. So essentially 3 realizations. -1, 0, and 1. -1 with probability p, 0 with probability q, and 1 with probability 1 minus p minus q. And then we can write the probability mass function simply as, so the smaller subscript x means that our probability mass function refers to our random variable x and is evaluated at a particular realization value. And the mapping is as follows: p if x is equal to -1 and so on, of course. And our support is -1, 0, and 1, the set of realizations, as I already told you. And why do we do all of that? Well, because we can derive a lot of quantities out of a probability mass function in a random variable. For example, an expectation value. So, for example, when we can calculate the expectation value of this scenario, which is equal to, so we have to sum over all realizations which are in the support Rx, and multiply that x with the probability mass function evaluated at x. It gives us minus p plus 0 times q plus 1 minus p minus q times 1 is equal to, and if we plug example values, for example, p is equal to 0.2 and q is 0.3, it will give us 0.3. And this makes sense because we have -1 with a probability of 0.2, 0 with a probability of 0.3, and 0.5 with that we get 1. So of course we would expect that our expectation value is greater than 0, and it's exactly 0.3. So thanks you for tuning in to Statistics 101. See you in the next episode when we talk again about statistics.